3. Graphs that enlighten and graphs that deceive. To begin with the graphs that enlighten, we have a dot plot, and that's a graph of quantitative data where each data value is plotted as a point or a dot above a horizontal scale of values. If dots have equal value, then they are stacked. So something similar to, let's say, the numbers 1, 2, and 3 in here. And we have entries as such. So all of the values are stacked if we have more than one frequency of that value. It displays the shape of the distribution of the data, and it's usually possible to recreate the original list of data points, especially if there's no rounding or anything like that going on. But, as you might notice with this, if we are indeed using a dot plot, these, for the most part, have to be discrete data. And for the most part have a relatively small set of values that it could be a part of. Otherwise you'll have graphs you can't really tell a shape of at all. So something like this, which is used here with a this is used with a continuous data. Notice how with the way that this graph here is made, we wouldn't really be able to tell what the values here are, since we'd have that continuous data, and they would have to be rounded pretty much in order for us to determine where specifically to put it inside of this plot. But this is of the pulse rates and the beats per minute of males from this body data dataset. As you can see, again, this being a continuous dataset, but because we, one, have to round, and number two, have these points between the data values, this one will be harder to read than this one here was. So a discrete data set like this one is a lot easier to read as a dot plot than a continuous one like this. A stem plot, or stem and leaf plot, represents quantitative data. The stem is the rightmost digit, usually, and the left is the rightmost digit. A legend indicates how to read the data, and better stem plots are rounded first. We can expand them, condense them, or split them. It shows the shape of the distribution, for the most part, retains the original data values, and the sample data are sorted and in order. So let's say, for example, we have the values, I don't know, 10, 11, 15, and 20. We could form our stem and leaf plot with our stems being the tens digits, so 1 and 2. We have a leaf for the tens digit here with 1. The ones digits, we have a 0, a 1, and a 5. No commas. And for the 2, we just have 20, so this is a 0. And when I say a split stem, this occurs when we have in the first range of leaves, we would have the numbers between 0 through 4, and the second between 5 through 9. That's what I mean by a split stem. So for example, using that same pulse rates of males data set from example 1, we can have ourselves a stem plot here. And as you can see, this one, however, is not a split stem, since all of them are still plotted out on here, and you can definitely see that shape of this distribution is roughly approximately normal. Again, we have a little bit of variation here, but we could definitely see a roughly normal distribution here. We have a time series graph, and this is a graph of time series data, or quantitative data collected at different points in time, and it reveals information about trends over time. So at this graph down here, depicts the yearly number of fatalities of law enforcement officers in the United States. And we have a spike right here, which corresponds to the September 11th, 2001 terror attacks. So, except for the data from 2001 that I highlighted, there appears to be a downward trend, right? Here we have close to 180, and down here we have closer to 120. Though the lowest happened here, which was closer to 100. A bar graph uses bars of equal width to show frequencies of categorical data. It shows the relative distribution of categorical data for comparisons. And one of the more well-known bar graphs is a Pareto chart. That's a bar graph for categorical data arranged in descending order of frequency. It specifically draws attention to the more important categories. And for the accidental deaths in a recent year, we could see in this Pareto chart that the deaths from the poison category represent the most serious problem. And that's deaths from poison include deaths from drug overdoses as well. And notice the second one there being motor vehicles, drowning not being as frequently seen. A pie chart is a common graph that depicts categorical data as slices of a circle that are proportional to the frequency count, and indeed that percentage if we did a relative frequency for the category. It's not as effective as a Pareto chart, however, since, especially when you have several pieces like we do here, it's kind of hard to determine what these percentages actually are without that data inside of the graph. But it does show the distribution of categorical data in a commonly used format. But despite that fact, it's still not as nicely viewable as a Pareto chart. We would never use pie charts, however, because they waste ink on components that are not necessarily data, and they lack an appropriate scale. And as you can see, they do indeed color these in different parts. So something like a black and white printer isn't going to display this as nicely as a colored printer. But that pie chart there is on those accidental deaths. A frequency polygon uses line segments connected to points located directly above the cross midpoint values. It's very similar to a histogram. A relative frequency polygon uses the relative frequencies for the vertical scale, and two or more can be combined in a single graph for comparisons. And always these are easier to be judged than the frequency charts being in the same tables. The frequency polygon here corresponds to the full IQ scores of the low lead group, as the heights of the points correspond to the cross frequencies, and the line segments are extended to the right and left, so that the graph begins and ends on the horizontal axis. The plots are pointed directly above the cross midpoint values, as we can see here. For a graph that deceives, one of such ways is a non-zero vertical axis, like this one. That way we could see if the vertical axis begins at a non-zero value, so the differences are exaggerated. Like here, oxycontin appears to be way higher than a placebo for the percent experiencing nausea. But if we actually graphed it with a 0 percentage on the y-axis, notice these are always a lot closer together. Mind you, the oxycontin one's still much greater, but not nearly as big of a difference. A pictograph is another graph that deceives. It's a 2D or 3D picture drawn on a 1D graph, and it could cause distortions. You could also, for example, the way that these cigarette butts here are graphed, this one says 30% of US adults smoked, here it says 18%. This one appears to be double both the width and the length, which means that the way that the percentage here is displayed, this percentage should be much higher than it actually is. But in this case, it's not. So these particular graphs, the way that they're displayed, since they're supposed to be a three-dimensional image, they do not accurately judge the size in the way that these percentages here are. And as such, they distort the data. In summary, and these are from the Visual Display of Quantitative Information by Edward Tufte, for small data sets of 20 values or fewer, a table tends to be better than a graph. A graph of data should make us focus on the true nature of the data, not on other elements, such as eye-catching but distracting design features like 3D especially. Do not distort the data. Construct the graph to reveal the true nature of that data. And almost all the ink in the graph should be used for the data, not on design elements. Thank you.